In this video, I'm going to take a closer look at the properties of the character tables. And so these are the properties of the character tables that I used in previous videos to sort of derive the character tables. And so the properties were things like the dimension or the sum of the dimension of each of our irreducible representations, which we'll call G alpha. When we summed those together squared, that was equal to the dimensions of our, or the order of our group. And we also showed that that when we sum together the characters, or the square of the characters of our group, so the chi of our group R and squared, that was also equal to the order of our group. And we also showed that we just sort of used the fact that the number of irreducible representations in a group cannot exceed the number of classes. And so the number of irreducible representations in a group, so we can call that, I guess, chi R, has to be equal to the number of classes in the group. And so in this video, I'm going to sort of kind of go through and mathematically show why this is the case. So like I said, we've used these things in the past, and now I'm going to kind of mathematically show that these things are actually true. All right, so if we have a group G which has order of G between the two bars like that, and two equivalent irreducible representations which are related by this similarity transformation here, then the trace of those two irreducible representations have to be equal to each other. That's because if we have our representations here related by this similarity transform, we can then sort of do matrix multiplication on both sides with the x. So this x minus 1, or this inverse, will get canceled out because it will just become the identity element with x. And so we have this relationship here. And we know from the previous video using Schur's lemma that then that has to be equal to some scalar multiple of the identity matrix. So then if we sort of take the inverse of this beta representation here on both sides, we have d alpha with our x, then d beta inverse equaling some scalar multiple of the identity matrix. And so we take the trace of both sides, and that will end up being some scalar multiple times the trace of the identity matrix. And so that, like I said, was using Schur's lemma to show that the trace of these two irreducible representations that are equivalent to each other have to be the same. And so that means that these are the same. And this leads to the property of the table of each irreducible representation is orthogonal to each other, or otherwise they could be related with a similarity transformation. Since we have that the trace of a matrix representation of symmetry operations is the character of the operations, we can then make this relation. So the trace of our d alpha irreducible representations is equal to this chi alpha character, and the same for our d beta and chi beta here. And we said in a previous video that an n-dimensional irreducible representation of a group G, which has order, that we're going to use this lowercase g, has vector lengths that were like this. So I talked about this briefly in a previous video. So we sum up the products of these two representations here, and we end up with this G divided by the dimensionality times all these Kronecker deltas here. And so the orthogonality means that we can set this I equal to J and this K equal to L, so we have I and KK here. And so that equals this G over N times these two Kronecker deltas. And so we have that if we sort of multiply through, and so that's essentially taking the trace of these two things for each of our representations, that will equal this right here. And so we have this summation along this this Kronecker delta here, which is ones only on the diagonal. And so if we just take the sum of the diagonal, that will equal the dimensionality, because it's a m by m matrix, and so the trace where it's ones all in the diagonal will equal the dimensionality of that matrix. And so then we can take what we got up here, which is put down here again. And so we can see that our g over n, this Kronecker delta, and this n here, because we are substituting that in right there because of this relationship right here, these n's will cancel out, and so we just have this being equal to g here. And so summing on the left-hand side over I and k gives the product of the traces. And so it must be that if we have the summation of the product of these traces here, that we said that that equals this g delta alpha b. And so we have this here. And so that is sort of showing that that property that we use that I talked about before, that if we because we said that the d alpha and the d beta have to be the same, and so that was showing that when we take the sort of character of each thing squared and sum over it, so we sum over it, that is going to be equal to the order of our group. And so that's what we are showing right here. And so if this does equal the order of the group, that tells us that our d alpha, or the character of our d alpha and the character of our d beta here, being equal. So it's a sufficient condition for two representations to be equivalent. Otherwise, we could do this and get 0, which is impossible. All right, so I have these things in the different colored boxes because they're each talking about sort of a different property of our table. And so now that we've kind of shown this to be the case, we are now going to move on to a different one of the properties. And so we've defined in a previous video the direct sum like this, and so it's essentially just taking each irreducible representation and sort of putting it into a large matrix that is a block diagonal of each of the matrices of those irreducible representations. And so there will be this n here number of each of these irreducible representations in our D here. And so where n alpha are how many times the irreducible representations show up in the diagonal blocks. So how many equivalent irreducible representations there are, and everything else. So over here and over here is 0. So that's just the definition of our direct sum. And so the character of D is the sum of the characters of each of the matrices in the direct sum, which makes sense because if we have all of these in this diagonal here, then if we just take the trace of this entire matrix here, then it will just be the sum of the traces of everything in the block diagonal there. And so we have this character for our sort of full direct summed matrix. And if we multiply this right here by just one of the characters and sum over I, so this thing is essentially picking out the sort of chi alpha representations in this right here. And so we multiply those two together and sum through, we end up getting n alpha times g, because g is going to be the order of it, and n alpha is how many times we have this thing showing up in there. in our sort of, giant matrix of everything sort of direct summed together. And so then we can divide through by G here, and we end up with this. And so this was that thing I was using in a previous video to find out how many of these equivalent uh, irreducible representations are in our group. And so in that video I looked at the C2V, and I found, I don't remember offhand, but it was something like 3A1s plus 1A2 plus, I don't remember, something like 2B1 plus 3B2 or something like that. But so we just found these coefficients. This would have a 1 there and a 2 and so on. So we just found those coefficients, and that's how many times these irreducible or equivalents of these irreducible representations actually show up in our group there. All right, so for instance, if we want to look at this a little more concretely, we can actually look at our C3V example group. And so in a earlier video, we got this as 3 different representations of the group. And so if we take the direct sum of just the D1 and the D3 up here, we're essentially just taking this 2 by 2 and this 1 by 1 matrix and sort of just stacking them in the diagonal. And so for instance, with this one we have this 1 here, and then this 1 diagonal here, and so we now have that right there and that right there. And so that's what we're doing when we do the direct sum. And so we do that for each one of these symmetry operations. And so that gives us this, where this here is the character of these 3 by 3 matrices here. So that is a reducible representation, and these are characters of our 2 by 2 and our 1 by 1 representation there. So this bottom row being our 2 by 2 irreducible representations, and this one being our 1 by 1. And so we can put that into a table like this, and so what we see is that the irreducible representations 2 plus 1 is equal to 3. So the character of each of these for each class here is equal to this reducible representation, which makes sense because that larger representation is just a diagonalization of the 2 smaller representations there. And so it makes sense that those would be equal to each other. So the sums would be equal to each other. All right, so once again, sort of changing direction here. So we can generate what's called the regular representation of our group G by making a representation of dimension equal to the order, where the group elements act as basis vectors. So this means that we map each element of our group onto a G by G matrix. And so for instance, if we are using the C3V group, which has 6 different symmetry operations, it would be a 6 by 6 matrix. And it's a matrix that has only that has a 1, and then everything else is a 0 in it. Like so we might have, something like this, and so maybe something like that. So each column only has a single 1 in it, and so these act as sort of permutation matrices. And so in the previous video, or maybe a couple videos ago, I don't remember what it was, we saw that matrix that was like 0, 0, 1, then like 1, 0, 0, then like 0, 1, 0, and we saw that just sort of permutated the basis vectors. And so we are looking at sort of a G by G matrix that does kind of that same thing. And so they are permutation matrices. So only the identity element E will have 1s going down the diagonal, because that has just a single 1 in each column, and it's the identity, so it has to go down the diagonal. And so the character of it will be equal to the order of the group, and we will actually have that the character of anything else that's not equal to the identity element is equal to 0. And so we can take this chi sub alpha here for an irreducible representation d alpha that has g alpha dimensions such that the character of its identity will be equal to its dimensionality. And the number of times d alpha occurs in our regular representation d will be the direct sum like this. And so we can actually find out how many times it's in there by just taking the alpha version, which is some other dimensionality, times the dimensionality of the regular representation. And so, for instance, like if this chi alpha was 3 dimensions, and then this regular representation was 6, it'd be 3 times 6, but then we are dividing here by the dimensionality. So that effectively just cancels those two things out. And so it just ends up being equal to the character of the alpha g. And so that is equal to the g alpha. And so every g alpha dimensional irreducible representation, d alpha, occurs just g alpha times in the regular representation d. And so since we just showed that the character of that identity in the alpha irreducible representation is equal to g alpha, and a d alpha occurs n alpha equals g alpha times, that means that our n alpha times the character is equal to n alpha times g alpha. And so summing over each, we get that the character here of our regular representation is equal to the sum of the n alpha times g alpha, which since we said that n alpha is equal to g alpha up here, we can substitute a g alpha in for that n alpha. We get this g alpha squared. And so we see that the identity equal, so we just change this identity for g down here, and we see that the order of our group is equal to the sum of the dimensionalities squared. And so for instance, in our C3V, we had that, so we remember we had I think we had an A1, a B1, and then an E, where this has dimensionality 1, this has dimensionality 1, this has dimensionality 2. And we said that if we have 2 squared plus 1 squared plus 1 squared, so that's 4 plus 1, so 5, 6, that equals 6. And that is actually the order of the C3V group, because we have the identity, we have the C3 and the C3 inverse, and we had the three sigmas, sigma 1, sigma 2, and sigma 3, and so it has 6. It's an order 6 group, and so this is just telling us that the character of the identity of our group is going to be equal to G, and that will be equal to the dimensionality of each of the irreducible representations squared and then added together, which, like I said, is another one of those properties we used in a previous video. All right, so kind of changing gears again here. So if we have a group, if we group our representations into H classes, which we will denote by C sub J, this should actually be in N right here. So N. And so we're just saying that the number of classes is less than or equal to the number of symmetry operations, because we have to take the symmetry operations and group them into classes, so you couldn't have more classes than symmetry operations. And if we have that each class has H sub J elements in it, where the J here ranges between 1 and H, then we have that the sum of these two characters here is equal to, so now we're inserting this here, which is the number of elements in a class, and so we're taking the characters of these classes, and so that should still be equal to our G here, assuming that the chi alpha and chi beta are the same. And so what we're doing, because these have we're taking the uh, the character of those representations, but over here we are grouping those representations into classes, but then we have to multiply by the number of elements in each of those classes as we sum over J. And so that gives us this right here, where if we divide by G, so we divide through by G on both sides here, that this just equals the Kronecker delta. And so then we split this up into two different sums, and so we have to make that into these square roots right here, and we have our characters of the classes right there. So these here, the sort of square root of the number of elements in the class divided by the order of the group times the character of the class. So these are the normalized character vectors with components, which are these, forming an orthonormal set in a space of h dimensions. So a space of dimensions that is equal to the number of classes that we have. So each irreducible representation has one such vector, and so the number of distinct irreducible representations cannot exceed the number of classes. And so that is that other property that we used, where we said, if we have, like, so in the C3V, for instance, we have our identity, we have our 2C3, and then we have our 3 sigma V. And so we said from this that we have to have only 3 different irreducible representations, which was our A1, our B1, and our E. And so the number up here, this should actually be more like this. So A1, B1, and E. So the number of irreducible representations here can't exceed the number of classes there. And so we can actually calculate these components here, these vector components for our C3V group. And so we have our A, B, and E irreducible representations here. And so when we multiply by the number of elements in the classes over G, so the square root of that times these characters here. So then we just put the numbers in. So for the E, there was only one element in the class, so it just has the 1 there. There are 2 elements in this class, so these have the 2's there, and 3 elements in this class, so it has the 3's there. And so we just calculate those, and we end up with these. And so we have an orthonormal basis vectors in a unitary 3 space that have these components right here. So these 3 vectors form an orthonormal basis in this 3 space, because 3 is the number of classes that we have. But anyway, the sort of takeaway message for this one I have here in pink is essentially just that the number of irreducible representations has to be equal to the number of classes that we have. For the purple up here, it was this. It was that the order of our group has to be equal to the dimensionality of our irreducible representations squared and then added to each other. So what we had up here in green, the main takeaway message was just how to calculate the number of those equivalent irreducible representations in a group. And so what we had up here in blue was just this, where if we just, because the chi alpha and chi beta have to be the same, this is essentially just taking the characters squared and adding them up, and we end up getting the order of the group. So that'll, when we add those up, it will be equal to the order of the group. But anyway, like I said, this was just sort of a mathematical way of showing that those properties that I was using in a previous video to sort of derive the class or the character tables rather, we can sort of mathematically show that those things are actually true and they're not just sort of numerology or something that we're just pulling out of thin air. But anyway, I hope you found this video helpful, and I will see you in the next one.